Hello, my name is Santiago Mol Lopez, and in this video about derivatives, we are going to review the derivatives of the functions arctangent, arc-cosine, and arcsine applying the chain rule. The requirements are quite minimal. You simply need to know the derivatives of elementary functions. Let's begin by creating a table with the derivatives of the functions arctangent, arcsine, and arc-cosine. We'll start with the derivative of the function arctangent of a certain function g of x. If someone were to ask you to calculate the derivative of arctangent of x, not g of x, you should state that it is 1 over 1 plus x squared. This is one of the derivatives you should be familiar with. So, how do you calculate the derivative of arctangent of a certain function g of x? The derivative would be 1 divided by 1 plus the function g of x squared multiplied by g prime of x. However, there are two important points to note. First, the square in g of x squared is a result of the formula. I previously mentioned that the derivative of arctangent of x is simply 1 over 1 plus x squared. In this case, when it's not x but g of x, the square comes from the formula. The second point to emphasize is that in this formula, we multiply by the derivative of g of x. It's a common mistake to calculate the derivative of g of x squared, but that's not the correct approach. Instead, you should calculate the derivative of the function within the parentheses after the arctangent. Let's explore the derivative of the arcsine of g of x. In this case, it's the same principle. What is the derivative of the arcsine of x? It would be 1 divided by the square root of 1 minus x squared. Since we have g of x instead of x, its derivative would follow this pattern. 1 divided by the square root of 1 minus the function g of x squared, and then we multiply by the derivative of the function. It's crucial to remember to derive only the g of x function, because it's a common mistake to try and differentiate the square root of 1 minus g of x squared, which can be quite complex. Now let's examine the arc-cosine of g of x. I won't go into much more detail because it's very similar. In fact, the only difference, as you can see, is a negative sign. By the way, an important note I haven't mentioned so far is that the arctangent, arcsine, and arc-cosine functions are the inverse functions of the tangent, sine, and cosine functions, respectively. We're going to look at a few examples and apply the rules we've just discussed. I'll display the formula again because we'll need it, and I want you to have it in front of you with each example. Let's calculate the derivative of the arctangent of x squared plus 2x plus 1. First, let's identify g of x, which is x squared plus 2x plus 1. Now, let's apply the rule. If you notice, we would have to put 1 over 1 plus. 1 over 1 plus. So far, it's the same. Now, the function gx is all of this. So I take the entire expression and square it, because the formula tells me to square it. Then, I multiply by the derivative of the function g of x, which is the derivative of this function. What is the derivative of x squared plus 2x plus 1? It's very simple. The derivative of x squared is 2x, the derivative of 2x is 2, and the derivative of a constant which adds up is just 0. Let's put together more things. What is the derivative of the arctangent of the sine of x? It's very simple. If we identify that g of x is the sine of x, then we would have that the derivative would be 1 divided by 1 plus the sine of x squared. Notice that I take the function that was here and I square it here in the denominator without differentiating it. Then I multiply by the derivative of the sine of x. You should all remember that the derivative of the sine of x is the cosine of x. Let's now examine an example involving the arcsine function of g of x. In this case, as we discussed earlier, its derivative is 1 divided by the square root of 1 minus g of x squared, multiplied by g prime of x. One example. What if someone asked us to calculate the derivative of the arcsine of x cubed plus x squared? In this case, if we identify g of x as x cubed plus x squared, how do we calculate the derivative? By applying the formula directly. It would be 1 divided by the square root of 1 minus the function that was in parentheses squared without differentiating it. Then, we multiply by the derivative of g of x. I insist, this has nothing to do with the expression in the denominator. It is the derivative of the function within the parentheses. The derivative of that function is 3x squared. The exponent goes down and we subtract 1 from the 1 that was there, plus 2x, which is the derivative of x squared. Now, let's look at another example. What if we were asked to calculate the arcsine of the square root of x? In this case, what is g of x? G of x is the square root of x. What is the derivative of the square root of x? It is 1 divided by 2 times the square root of x. If we apply the formula, we would have 1 divided by the square root. There's a mistake here. I hope you noticed that it should be a minus instead of a plus due to the formula. It's 1 minus the square root of x, and this function remains exactly the same here. Squared, and then multiplied by the derivative of the square root of x. What is the derivative of the square root of x? It's 1 divided by 2 times the square root of x. In this case, we've made a slight adjustment, and the recurring mistake here is that the plus should be a minus. All we've done is reformat the denominator by placing the square root of x at the beginning. Additionally, we acknowledge that the square root of x squared is x, although technically it represents the absolute value of x. For simplicity, we'll use x. Let's now explore examples involving the arc-cosine of g of x. Recall that the only difference from the previous case is the introduction of the negative sign. Everything else functions in the same manner, so the examples should not be overly complex. What is the derivative of the arc-cosine of x raised to the power of minus 2? It's quite simple. The function g of x is x to the power of minus 2. Therefore, when applying the formula, we get minus 1 over the square root of 1 minus x to the power of minus 2 squared. This is essentially the same function that was enclosed in parentheses, squared. Then, we multiply by the derivative of this function. What is the derivative of x to the power of minus 2? The negative exponent does not change how the rule is applied. The derivative is calculated as follows. The minus 2 comes down, and 1 is subtracted from the exponent. So, if it was minus 2 before, after differentiation, it becomes minus 3. And that's our result. We can simplify it further. When you multiply the two negatives, one from the exponent and one from the formula, they become a positive sign. So the expression becomes 2x to the power of minus 3 divided by the square root of 1 minus x to the power of minus 2 squared. Let's proceed with another example. Arc-cosine of e to the power of x. We mix now the arc-cosine function with the exponential. How do you calculate it? If you identify that g of x is e raised to the power of x, then simply apply the rule again. You would use minus 1 divided by the square root of 1. It's important to note that, similar to previous cases, there's an error where the plus sign in the denominator should actually be a minus sign. Please be vigilant about this mistake as it occurs frequently. The function e raised to the power of x is retained exactly the same and squared and then multiplied by e raised to the power of x, which is the derivative of the exponential function. You can simplify it by using e raised to the power of x in the numerator and remember changing the plus to a minus in the denominator. What have we covered so far? We've reviewed the chain rule with the arc-cosine, arcsine, and arctangent functions. I hope this has been helpful, and thank you for your attention.